Okay, now we get to some of the tougher ones. When we titrate a weak acid with a strong base, we end up with a salt and water like normal when you have an acid and a base. The thing is, the salt that we create in this case is going to be a basic salt. So we create the salt, and then the salt goes on to hydrolyze. And we saw that several lectures back. So we know that the salt that we create will be the salt of a weak acid and a strong base. So it's going to be a basic salt. It's going to create a basic solution, so the pH should be greater than 7. And that's what they're saying. So let's take a look at here. What is the pH of 50 mils of 0.1 molar acetic acid solution that has been titrated with 0.2 molar sodium hydroxide to the equivalence point? So we're going to reach the equivalence point where we've completely reacted all of the acid with just enough base to finish it off. So there's no acid or base left, just the salt. Okay, so we're titrating, which means we're going to have to convert to moles. So that's the first thing that you want to do. We're going to be first determining how many moles of acetic acid are present in this sample. So this is the beaker that's, I got to put in, I'm just going to make this HA. This is sitting in the beaker of, 50 mils are sitting in the beaker, and then we're titrating, we're putting sodium hydroxide in. And so there is this many moles of HA, of the acid. This is HA here, just to simplify things. And at the equivalence point, that means that, so at the equivalence point, we're going to have the same number of moles of sodium hydroxide. So if we take the number of moles of sodium hydroxide that have to be present at the equivalence point, we just determined that, divide by its volume, or its concentration, we get the volume of sodium hydroxide that we have to add. So that's, up until this point, we didn't know how much sodium hydroxide had to be added. Now we know how many moles of sodium hydroxide need to be added, and that's part of a 0.2 molar solution. So if we divide the moles of sodium hydroxide by its concentration, we get 0.025 liters of sodium hydroxide. This is important because since we're adding the volume of sodium hydroxide to it, we're changing the total volume, which means we're changing the concentrations that we're eventually going to plug into that final equation. So we need to know this. So we have this, so our total volume is 0.050 liters for the acid, and then we've added 25 mils, or 0.025 liters of the base. So there's our total. We're going to be, and we'll be using that later. So we'll remember that. Now, the acid and the base, and we'll just put the OH minus for the sodium hydroxide, goes to H2O and the conjugate base. And I guess let me write it out so that we have acetic acid. I don't want to abbreviate it too much. That's our HA. And then we have sodium hydroxide. Might as well leave it in that form too. They react together to produce water and sodium acetate. And this is the salt. So these are equivalent. We're at the equivalence point, so these are going to be used up. We'll have nothing but this salt, and then that salt is going to go on to hydrolyze. So let's do this out. We have, we're in moles, so this is 0.00500. This is 0.00500 moles, and just don't have enough room there. Now we're at equivalence, at the equivalence point, so it's the exact same number of moles of each, so they both get wiped out, both used up, and we're left with nothing but the salt. Okay, so we have 0.005 moles of the sodium acetate, and it's the acetate ion that we're after. And then we need the concentration of the sodium acetate is going to be this divided by the new volume. So that's why we had to find that volume. So a lot going on here. This is 0.0667 molar, and I'm just going to put the acetate ion. Now we're going to need another piece of paper. The sodium does nothing, but we know that what the acetate ion does. The acetate ion is going to react with water. It's going to hydrolyze to produce acetic acid. It's an equilibrium between the acetic acid. It's going to lie, whoops, it's aqueous. It's going to lie to the right for now because there was no acetic acid, but we're going to put some of, it's going to go in, it's going to produce some of the acetic acid and then OH minus. And there's the OH minus, that's why it's going to be, I said earlier, it's going to have a pH that's greater than 7. Put this number in, we have 0.0667, and now we're back to a problem that we've done many times. So these buffer problems, these titration problems, they all require a huge amount of setup, but then after we get through that, we just get back to our original minus x plus x plus x kind of problems. Now, this is producing OH minus, so this is a Kb expression, and Kb, we don't have a Kb for the acetate ion. That's, we don't have it in a table. So we're going to take Kw divided by the Ka for acetic acid. So this is 1 times 10 to the minus 14 divided by 1.7 times 0 times 10 to the minus 5. And Kb is 5.88 times 10 to the minus 10, and that's what goes here. Now, I'll trust that you can determine that X is the concentration of OH minus, which is 6.26 times 10 to the minus 6 molar. And that gives us a pH. Again, I'll trust that after all of this time you can convert this to pH, 8.80. It's greater than 7. It was supposed to be. It seems reasonable considering the concentrations that we have. And that is the deal. So let's do another one. Always try to do 2 here. Okay, so we have a weak acid again. We have a strong base. Okay, so this one's a little trickier because we have the strontium hydroxide, but there are 6 strong bases, 3 that have OH minus, just 1 OH minus, and 3 that have 2 OH minuses. So I like to use both of them. Both types. Don't want to shy away from it just because it's a little trickier. But since we're titrating, we're going to have to determine the moles of the acid. And for this one, I think I'll use the full name because I used it last time just so that there wouldn't be any misunderstandings about what we were doing. But this time, it's just a short name. So we have OH, we have 0.01 moles of the nitrous acid. We're going to need the same number of moles of OH minus to react with it. And just like I did before when we're dealing with a strong base with 2 OH minuses, I'm going to just deal with the OH minus. So we have 0.3 molar strontium hydroxide is equal to 0.6 molar OH minus. So this is the concentration of this base, but inside of that solution it's 0.6 molar OH minus. And it's really the best way to go about dealing with this. You can try it another way. There's more than one way to do this, but we're going to take the concentration of the strong base as is and then convert it over to what is the true concentration of OH minus, because that strontium hydroxide breaks up, it ionizes, and it forms 0.6 molar OH minus. So this will give us the volume that we'll need of the strontium hydroxide to have enough OH minus to neutralize the acid. And so the total, now I know this is a bit of a tricky step. In my class you want to contact me if you have any trouble with it, but it's easier than dealing with strontium hydroxide just on its own. I tried it a couple of different ways when I was preparing the lectures. I always do it out this way for for my on-ground lectures, but yeah, it's just the best way to do it. Convert to OH minus for take strontium hydroxide and convert to just concentration of OH minus and use that from there on in to determine the total volume. Okay, ICE, we have 0.01 molar, and you might be able to see again that there's another shortcut here. So, well, why do I have to do this each time? You don't. You know that it's going to be 0.01 molar of the nitrite ion. So you can skip over this if you want. I'm doing it out just so you can see where that nitrite ion came from when we plug it into our final expression. So for here, you could just draw this equation to show what's going on, and then say it has to be 0.01 molar nitrate ion. Now we need to know the concentration of the nitrite ion because that's what's going to go on to hydrolyze. Divide by the new volume, and we end up with 0.176 molar nitrite ion. And so NO2 minus plus water, it hydrolyzes. Now there was a strontium ion, but that's not going to do anything, and that's why we got rid of it, because we didn't want to have to deal with it. That nitrite ion will try to get it back into the form of nitrous acid. That's where it's happiest. And in the process, it's going to produce an OH minus. And so we put in 0.176 molar. This is 0, 0, minus x, plus x, plus x. Back to the original type of problem that we've done before. I think I got enough room here. X squared is 0.176 minus x. And this is going to be a KB the KB that we have here is going to come from KW divided by KA. So that's 1 times 10 to the minus 14 divided by the Ka for this expression is, this is for nitrous acid. Ooh, I don't know if I have that sitting around handy. Of course not. Hold on. Actually, I have the KB number, but I want to have, nitrous acid is 4.50 times 10 to the minus 4, and that gives us a KB of 2.22 times 10 to the minus 11. I guess I didn't have to do that, but I just wanted to show you where this KB comes from. And then X is equal to the concentration of OH minus, which is 1.98 times 10 to the minus 6 molar. And your pH from that is 8.30. Should be greater than 7 because it creates, what we created is a salt that has a weak acid and strong base parent, or set of parents. So it should be a basic salt. So when it goes into solution, after creating it, it should hydrolyze to produce a pH greater than 7.